Alright guys, today we are going to talk about the ideal gas law, making our way through all of these different gas laws. Right. So far we have always assumed the number of moles of gas remain the same. For example, in a car tire, a balloon, a 2-liter bottle, what happens? So those are all closed systems. Alright. So if I take a car tire and I heat it up, the number of molecules of air, for example, that are inside that car tire has not changed. They're moving faster, they're at a different temperature, they're at a different pressure, they may be even at a different volume, like if we have a balloon. Right? But bottom line is, I have not changed the number of molecules that are in there. What happens when I fill a tire? Or I fill a scuba tank? Or I use an aerosol can and I spray some stuff out of it? Right? I'm changing the number of particles that are inside the can or the canister. Right? So that's something that is completely different that we haven't dealt with, is the number of moles of particles in a system. Well, we go back to Avogadro. If you remember Avogadro, he's the guy about the mole concept. And he said that equal volumes of gases at the same temperature and pressure contain equal numbers of particles. So he said, this is the 22.4 thing. He says, if I have a box, and it's 22.4 liters, and it's at a particular temperature, and I have another box right next to it, and it contains a different gas, it's exactly the same size, exactly the same temperature, then I'm going to have the same number of molecules in each one. Right? And he specifically said that 22.4 liters at standard temperature and pressure is 1 mole of a gas. Actually, he didn't say that, but we've come up with that. So, the ideal gas law uses that fact, and it says, the ideal gas law describes the behavior of an ideal gas. That's important. An ideal gas in terms of pressure, volume, temperature, and number of moles. So it's PV equals nRT, which we call PIV-NERT. So please write that down. PIV-NERT is one of those very important gas laws you have to memorize. Pressure times the volume equals the number of moles times R times temperature. What is an ideal gas? Well, let's go back to our kinetic molecular theory, and remember, this is by definition what an ideal gas is. The gas particles have virtually no mass. Right? They take up, I'm sorry, that's wrong. They take up virtually no space. Right? That one's wrong. They have mass. All of their collisions are elastic, meaning they bounce off each other all the time. They take up no space. They do not attract each other. That is key. They bounce off each other, and they don't sit down and attract each other and hold on to each other, because if they did, they'd become a liquid. Okay, so they don't attract each other, and they're in constant, rapid motion. They're always moving. If they didn't, they'd sink. So when does the ideal law not apply? Well, you have a couple of situations. You can be under high pressure, or you can be under low temperature. What happens in these situations? Well, let's say that you have a gas and you put it under really high pressure. Well, those molecules are getting closer together. So all of a sudden, remember the concept that the molecules take up virtually no space? Well, now all of a sudden, if that big, huge space between them is now just tiny, then the size of the molecule makes a difference. So that's a deviation from the ideal gas law. Right? So if we're under really high pressure, that's true. The other thing is if we're under really low temperature. If we're under really low temperature, the molecules are not moving quickly anymore. So they have time to grab a hold of each other as they go by each other. Think of it as two people walking down the hall. All right? And you have a person walking down the hall going in this direction, and you have another one walking down the hall going in this direction. All right? Well, if they're both running, they're not going to be able to grab a hold of each other as they go by. Or if they're both in vehicles, cars, and they're both going at 60 miles an hour, they can't grab a hold of each other. But if they're both walking slowly, that's your low temperature. If they're both walking very slowly, they can grab a hold of each other and stop and talk. And that's the problem, is if the molecules are moving really slowly, they'll stop and they'll hold on to each other. And that is not ideal. So if we have high temperature or low pressure, those take us away from the ideal gas law. So our ideal gas law, again, is PIV-NERT, PV equals nRT. What in the world is R? Well, R is something called the gas constant. It never changes. Now, it is dependent upon what units you're in, but it doesn't change over time. So, for example, we could have a gas constant of 0.0821, but notice your units. Your units here are in liters times atmospheres divided by moles in Kelvin. Now you'll notice in all of these we're dividing by moles in Kelvin. All of these other ones are 8.314, but notice your units on top. You could have pascals and cubic meters. You could have liters and kilopascals instead of atmospheres, right? So you have to decide which R constant to use based upon the units that you're using in your problem. So please write these gas constants down and write down the units, because that will become very important as we go into our next problem, which is here. Let's read the problem. A scuba tank takes up 64.5 liters. It's filled with air at 45.3 atmospheres and 25 Celsius. How many moles of gas are present in the tank? Well, the first thing we have to do is figure out what R constant to use. So let's look at our units. We're given liters, and we're given atmospheres, and we're given Celsius. Well, all of these are in Kelvin, so we're going to have to convert this from Celsius, from degrees Celsius into Kelvin. Well, that's always true. We got liters and atmospheres. Well, here we've got liters and kPAs, and here we have liters and atmospheres. So, folks, you could go through a conversion to use this one. You could convert your atmospheres to kPAs and then use this gas constant. But because this gas constant up here is already in liters and atmospheres, we're going to use that gas constant. Okay? So, that's the one you should be prepared to use. And we're going to go and do a plug and chug now into our problem. Right? Our problem is we have to do PV equals nRT. So what do we have? We have our pressure is 45.3 atmospheres. And our volume is 64.5 liters. Our number of moles is what we're trying to figure out. Our R constant, well, if we go back and we said we chose this first R constant that was here, the 0.0821, because it's in liters, atmospheres, moles, Kelvin, right? So we say 0.0821, and that's in liters, atmospheres, per moles, Kelvin. And our temperature, oops, we're in Celsius, so our temperature is 25 degrees Celsius plus 273 gives us 298 Kelvin. So our temperature is 298 Kelvin. Right? Now it's very important as you look at this. You'll notice we have Kelvin here and Kelvin here. We have moles here and moles there. We have liters and atmospheres on the left, and we have liters and atmospheres on the right. The beauty of this is they're all going to cancel. So when we do the math, we're trying to solve for moles. All right? So how do we do that? Well, it's pressure volume divided by R and T gives me N. So PV over RT gives me N. You should be able to do this algebraically. This is not rocket science. 45.3 ATMs times 64.5 liters divided by R, which is 0.0821 liters, atmospheres, moles, Kelvin. Let's see, what else do we have? We have temperature, and that's 298 Kelvin. All right, now why did I bother writing all the units? Because I always do, and I want to make sure my units cancel. For example, here I've got ATMs, and here I've got ATMs. Here I've got liters, here I've got liters, and here I've got Kelvin, and here I've got Kelvin. So I'm left with 1 over moles. Oh, well, if you divide by 1 over moles, that flips upside down, right? You divide by the inverse, so you divide by something, you flip it upside down, multiply by the inverse. So that gives us moles as our final units. So when I simply plug and chug all this into my calculator, my answer is going to be 119 moles. And I notice I have 3 units of precision there, 3 units of precision there, 3 units of precision in my Kelvin number. So I have 3 decimal places everywhere. My answer is going to have 3 decimal places. It's 119 moles. All right. All right, folks, let's try this one. We have a 12.4 cubic meter box, and it's filled with 809 moles of air at 35 psi. What's the temperature of the box in degrees Celsius? All right, so the first thing you need to do is pick your R value. So pause the video for a second and see if you can pick your R value. All right, well, the thing that I immediately notice is I've got a box that's in cubic meters. All right, now you might know how to convert between cubic meters and liters. Right? And you might know that there are 1,000 liters in a cubic meter, but you might not. So I would tend to just use this conversion factor right here because I have numbers in cubic meters. All right, so I have 809 moles of air. That's cool because everything's in moles, and I have 35.0 psi. My units here are in pascals, so I'm going to have to change that. All right, so let me do that right now before I go anywhere. I'm definitely going to use this as my R value, but remember that all of my units, whatever units I choose to use, must match the units in my R value. Okay, so I'm starting with 35.0 psi. And I want to convert from psi to pascals. You know how to do that? Go back and look at your old sheet. Make sure you know how to do that. Pause the video and do this. All right, we're going from psi. We can only go to atmospheres. And then from atmospheres, we can go to pascals, which is what we want. And 1 atmosphere is 14.70 psi. And 1 atmosphere is 101,325 pascals. And if I multiply this whole thing out, I get 241,250 pascals. And you say, oh, wait a minute, you can only have 3 sig figs. You're right. In my answer, when I'm all done with this whole thing, I'm only going to have 3 sig figs. But please don't round along the way, because if I round this to only 3 sig figs, I'm losing precision as I'm going along. All right? So don't do multiple rounding errors. Only round once when you're all the way done at the end. All right, I'm going to go to the next slide so I have a little bit more room. All right, same problem, and we are doing PivNert. And we have to solve for temperature. Notice it's in Celsius. We're going to get it in Kelvin. So our temperature is equal to pressure volume over number of moles times R. So our pressure, we just figured out, is going to be 241,250 pascals. And our volume is going to be 12.4 cubic meters. And our number of moles is 809 moles. And our R value is 8.314. And I'm going to write it out. It's pascals, cubic meters, over moles, and Kelvin. All right? Now, why did I write it out? Because I want to notice that my pascals cancel, my cubic meters cancel, my moles cancel, and I'm going to be left with Kelvin, which is what I want because I'm doing my temperature. All right, so if I plug all of this into my calculator and come up with an answer, I get 445 Kelvin, 444 point something. So anyway, 445 is Kelvin. I have to subtract 273, and that's going to give me Celsius. So my final answer is going to be 172 degrees Celsius. So that's my answer. All right, folks, I want to derive the combined gas law for you because I think this is really, really cool. Right? You have PV equals nRT. What's R? R is a constant. So I'm going to solve for R. PV over NT is equal to R. Now, if my constant never, ever, ever changes, so long as I keep my units the same, then this could be the initial state of my system. And then over here, I could say this is the final state of my system. So that tells me that this is looks like P1V1 over N1T1. Is it starting to look familiar? Is P2V2 over N2T2. So if my number of moles remains the same, as it did for Boyle's, Charles, Graham's, and the combined gas law, if my number of moles remains the same, the N disappears, and you're left with P1 V1 over T1 equals P2 V2 over T2. The beauty of all of this is it all fits together, and it all fits together so well, and that's why I wanted to show you how I can actually derive the combined gas law. Right? Now, in fact, you can, change the number of moles as well, and it still works. So either one of these two equations is really cool. Okay? All right. How do you know when to use the ideal versus the combined gas law? Well, PV equals nRT is what we've been using a lot, and P1 V1 over T1 equals P2 V2 over T2. Well, you use this one when something changes. Your volume's changing, your pressure's changing, your temperature's changing. That's when you use the combined gas law. But if nothing changes, if you have a static system, then you can use the ideal gas law. That's how you know when to use which one. If something is changing, you have to use the combined gas law. If nothing changes, you're using Pivnert. All right, folks, do the worksheets. Do them all. Take your time. Check the answers. Look at the answer key worksheets at the answer key podcast if you need to. All right, guys, you need to do these because it's the only way you're going to get familiar with these. All right. Have a good day. We'll see you in class. Ask us questions if you need to. And have a great time. Bye.